My name is Fergal O'Donoghue from IBM Research Europe in Dublin. Today I want to present work we did on using Julia to analyze environmental and fish dynamic data coming from an aquaculture farm. This work is in collaboration with partners from Dalhousie University in Canada, University of Stirling in Scotland, Gildeskål Research Station in Norway, and Cook Aquaculture in Scotland. Here we give an overview of the location of the aquaculture farm in the north of Norway. In this work, we use statistical and machine learning approaches to interrogate the environmental and fish dynamic data coming from a salmon cage. The data was collected using hydroacoustic sensors that sampled the vertical distribution of fish within a cage, while a network environmental sensors measured variables such as temperature, salinity, dissolved oxygen, etc. Here we see the farm itself consisting of a number of cages or pens, with each net pen consisting of about 50 to 100,000 fish. We used TSML, a Julia package for time series analysis to pre-process, curate, and interrogate the data and combine into a form amenable for machine learning. And we also used RCall to connect directly with R and the various statistical functionality there. So this gives an overview of the cage itself, consisting of a hydroacoustic sensor at the bottom of the cage looking up that samples the distribution of individual fish within a cage. So the data itself consists of the relative intensity or the relative distribution of fish within a cage. So this is a snapshot of the data from the hydroacoustic sensor, with the red or the hot portions here displaying regions with a high density of fish, and the dark circles here representing the average position of the fish cluster within the cage at each point in time or every hour. The environmental data sets that we use consist of a variety of metrics such as temperature, dissolved oxygen, salinity, and current speed, with a time series of the temperature and oxygen data sets presented here. One of the challenges of collecting data in the ocean is data quality and getting a continuous signal, with challenges due to power to the sensor and due to sensor damage or fouling, etc., and also with sensor drift, again due to biofouling, etc. So we combine sensor data with data from a numerically generated ocean model, the Nordkist 800 ocean model that generates gridded data at 800-meter horizontal resolution, and we extracted a same set of parameters from that to allow to augment sensor data when sensor drift was an issue or when data was missing. We complement this with weather data from IBM's Environmental Intelligence Suite, where we extracted data such as temperature, solar radiation, wind speed, etc., to inform on the effects of those on conditions within the cage. So here we visualize the environmental data, and just to give an overview of the similarity between sensor and numerically generated data sets from the ocean model, and the viability or feasibility of combining the data to give a better representation of the true signal and avoiding statistical imputation approaches and the risks for signal integrity from implementing some of those approaches. The final step related to extracting temporal features related to hour of day, day of year, etc., to inform the statistical and machine learning analysis. The statistical characterization of fish in a cage considered temporal variations and fish behavior in responses to external environmental conditions. Initially, we implemented statistical analysis of the data to understand how fish dynamics varied over the duration of the period, and to understand the different variations at hourly levels over at different monthly intervals. So here we have the box plot of hourly distributions of data for each month. So here we have June, July, August, September, and October. And it highlights slight tendencies towards day-night differences, which can be interrogated in more detail with a density plot that highlights that fish are slightly higher in the cage on average during the night than during the day. And similarly, during the day, fish tend to be more tightly clustered. The next step related to the machine learning based analysis of this to inform on which features drive dynamics and which features are more informative to the machine learning analysis, machine learning forecast and prediction, etc. So we deployed a random forest model with all available features. So these consist of temporal features, autoregressive features, and environmental features. And we reported quite strong model performance with the variance explained of about 76%, with the autoregressive features, or X1, X2, and X3 being the most informative, together with temporal features. In our next model, we reduced the features available to focus specifically on environmental drivers and inform on how those condition and contribute towards the variations and dynamics of fish in a cage. So a subset of selected features naturally return a drop in variance explained to about 60%, but more specifically, it provides a more interpretable model that is more interpretable model for the features present. So we can quite easily see that the features relate to salinity, temperature, and mechanical mixing, such as wind and current speed, have a high impact on predictive, or have a high feature importance, and that can be interrogated more completely with via the accumulated local effects interrogation to better understand how these vary at a clustered level as effect of salinity, sea surface height, current direction, and current speed. So for example, for sea surface height, we see that there's a almost linear relationship between variations in sea surface height and responsive from the cage dynamics. And finally, more details on this is available in our recent papers in Frontiers in Animal Science related to data-driven insight into fish behavior and their use for precision aquaculture. Thank you.